So we've been talking about connecting capacitors in series and then in parallel, but it is not uncommon to have some sort of both, a combination of series and parallel in the circuit. So as a reminder, series is when following a path you cross or you must cross all capacitors. So following a path from one end of a battery to the other, the capacitors you must cross are in series. In series, they will have the same charge. And then parallel is when we follow a path and there's a choice where we can pass one or another capacitor. In parallel, the capacitors will have the same potential difference. As we look at problems that have a combination of series and parallel, we will still be using our fundamental equation relating the charge on the capacitor to the capacitance and the potential difference. And we'll also do some examples after that will ask us to find the potential energy stored either in the circuit as a whole or by a single capacitor. So problems can come in a couple of different ways. I've sketched out a couple potential circuits that we're going to walk through and look at what we mean by series and parallel. In terms of problems that we are given, we could potentially be given a circuit like this first one on the left where we do not know the battery voltage, but we do know the capacitor values. And so I'm just making up some values here. So we have 3 capacitors, and they're connected to a battery that has a voltage value of 15 volts. And I'm realizing I might have said we didn't know the battery value. I'm a little tired at the moment. I apologize. Now, just another reminder about batteries. The long line representing the battery represents the positive terminal, and the short line represents the negative terminal. So to determine our series and parallel, you might see it right off the bat, which is great, but I'm also going to just follow the path because that can be helpful. So a path, all I'm doing is starting at one end of the battery, and I'm going to start moving through my circuit until I get back to the other end of the battery. So as I move through this circuit, I have to pass by the 10 microfarad capacitor. But then I reach a point right here that we call a junction. At this junction, I have a choice. I can only take one path at a time. So I can choose to go through the 5 microfarad capacitor back to the battery. Or if my path gets me to that junction again, I could choose to go straight and then down through the 15 microfarad capacitor. And that too will get us back to where we started. This junction, with having the 5 and the 15, the choice to go through either one, means the 5 microfarad capacitor and the 15 microfarad capacitor are in parallel. Now, one thing to mention, in the first path, as I went through the 10, I absolutely have to pass through the 10 microfarad capacitor regardless of the path I choose. And then if I go down the first branch, then I also have to go through the 5. So it might be tempting to say the 10 microfarad capacitor and the 5 microfarad capacitor in series. But that is not the case. When we talk about capacitors being in series, there can be no other option than following our path through those two specific capacitors. Since we have the choice to go through the 10 and then through the 15, that's why the 10 and the 5 are not in series. Similarly, the 10 microfarad and 15 are not in series either, for the same reason. We have a choice to go through and pass through either the 5 or the 15. So what we need to do is simplify our circuit and account for the 5 and the 15 in parallel. Now, to find an equivalent capacitance for capacitors in parallel, we simply add their capacitor values together. So 5 plus the 15, the 5 and the 15 in parallel are equivalent to having a capacitor that was just 20 microfarads. So what I mean by that, if I redraw the circuit, I have that 10 microfarad capacitor, but I could have just attached it to a 20 microfarad capacitor and still have the 15-volt battery. And the result would be the same. The circuit as a whole would still store the same amount of energy. So when we talk about an equivalent capacitance, we're just explaining what one capacitor could we use that would then take the place of, in this case, the 5 and 15 in parallel. Now, here with this new circuit drawing, if I follow a path through the circuit, I must pass by the 10 microfarad capacitor, then I must pass by the 20, and then that will get me to the other side of the battery. There's no other choice. As I follow the path, I must pass by the 10 microfarad capacitor and the 20 microfarad capacitor, which puts them in series. The process for drawing, or calculating, I should say, our equivalent capacitance when our capacitors are in series is this inverse relationship. So 1 over C equivalent would equal 1 over 10 plus 1 over 20 microfarads. So 20 to 3 over 20. But again, make sure we flip it because we have 1 over C equivalent. So the equivalent capacitance we're calculating is 20/3 microfarads. Okay, I'm going to move this guy to the right. Okay, what I mean now when we get this equivalent capacitance, that means this original circuit I drew with the 15-volt battery could have had just one capacitor attached to it, theoretically anyway, if that capacitor had a capacitance of 20/3 microfarads. Now, you can't buy every single possible value of capacitor. They don't make them all. You could potentially make your own if you wanted to. But if you were going to buy capacitors, you would only have certain values of capacitance to work with. And so this particular 20 thirds microfarad capacitor may not have been an option, which would be one reason why we might need to combine multiple capacitors together. In a problem like this, when we've been given the battery voltage and all the capacitor values, there's a couple different questions we could be asked for. One of them is, what is the equivalent capacitance of the circuit? If that were the question, then we would be done. But we could also be asked for something like, what are the charge and potential difference across each capacitor? So in this circuit, we know the battery is supplying 15 volts, but these individual capacitors do not individually have 15 volts across them. Charge moves around until an electrostatic equilibrium is reached, and we're essentially trying to find out how much charge is on each capacitor to get us to this equilibrium situation. Now, had this question been asked even before I got us to an equivalent capacitance, I still would have needed to figure out our equivalent capacitance. So my first step would have been getting to this equivalent capacitance of the circuit. And the reason why, if we think about the equation that relates charge, capacitance, and voltage together, when I have one single capacitor attached to a battery, in the equilibrium state, the potential difference across that capacitor is equal to the battery, which means the charge that accumulates on the plates of the capacitor is equal to the capacitance times the potential difference. Okay. Now, this is not the final answer we're looking for. This represents the charge that would accumulate specifically on the plates of this equivalent capacitor. Let's see what that goes, 5 times. So 5 times 20 is 100. That worked out nicely. So if I was to represent charges on this capacitor, both plates would have a magnitude of 100 microcoulombs on them. One plate is positive, of course, and one plate is negative. Okay, let's work back, because we ultimately want to find the charge and potential difference for each capacitor, meaning the original circuit. There were 3 capacitors. We want Q and delta V for each of them individually. So this is where these things that need to stay the same come into play. And let me see if I can move this guy completely off the screen. I thought I was being nice and prepared, but really I got in my own way instead. Come over here. There we go. So back to our circuit. This capacitance of, no, I don't want that tool anymore. The 20 thirds microfarad capacitance is the one single capacitor we could technically use to represent this same circuit. In order to determine charge and potential difference on all of our individual capacitors, we need to step backwards. So if I say the original circuit was circuit 1, this second circuit we created is circuit 2, this third one is the equivalent. So we went from circuit 1, we created circuit 2, we created circuit 3, which represents the overall equivalent capacitance. Well, to get back to charge and voltage, potential difference is the same as what I mean by voltage, and even energy, I have to work back through these same steps to do so. So from this circuit 3, I need to take a step back to circuit 2, and then from 2, we'll take a step back to circuit 1. Now, in terms of what we can take back to circuit 2 with us, that depends on what our equivalent capacitance was representing. So when we calculated this 20/3 microfarads, it was because we said the 10 and the 20 in this circuit 2 were in series. Well, if I go back to series, I know in series, these capacitors in series must have the same amount of charge. And that charge is the charge that their equivalent capacitance has. So we calculated over here in circuit 3 a charge of 100 microcoulombs. That means I can come to my capacitors over here in circuit 2 and say that both of these capacitors individually are storing a charge of 100 microcoulombs. They have to have the same amount of charge. The problem, these values we already have on here are capacitance. So now that we're in circuit 2, having capacitance and charge, same equation that we have at the top, I can solve for potential difference when I have capacitance and charge. So this top capacitor here, delta V, would be the charge itself, the 100 microcoulombs, divided by the 10 microfarads. The micros cancel, and then the coulombs per farad gives me a volt. So this capacitor right here has 10 volts across it. Similarly, for the bottom capacitor, Q is 100, divide by C, that's 20, we get 5 volts across this. And please notice, as we go around this circuit, this battery is a total voltage of 15 volts. As I pass from one end of the battery to another, the voltages across these capacitors that I pass have to add up to be 15. And that's what we're seeing. As I follow my path, this first capacitor has a capacitance of 10 volts. The second capacitor has a voltage, I might have said capacitance, I apologize if I did. So the first capacitor has a potential difference of 10 volts across it. The second capacitor has a potential difference of 5 volts across it. And then our path gets us back to the battery. So the 10 plus the 5 equal this battery voltage. This is a required rule that must be satisfied in our circuit. It's related to conservation of energy, though in and of itself it's not energy, but electric potential is related to the energy of a charge. Okay, so at this point, now that we have charge and potential difference for our individual capacitors, we're taking a step back again to circuit 1. So we have the capacitance. The 10 microfarad capacitor is the original capacitor in the first circuit. We now know this capacitor has a potential difference of 10 volts and charge of 100 microcoulombs. The 20 in circuit 2 is not the original capacitor in circuit 1. The 20 was equivalent for the 5 and the 15 in parallel. So going back to our rules for parallel, capacitors in parallel must have the same potential difference. So I come and I know we have calculated a potential difference of 5 volts on this equivalent. As I go back to these individual capacitors, they have to have the same voltage, not only of each other, but the same voltage of their equivalent as well. If I know the potential difference and the capacitance, I'm going to use our same equation yet again. Q is equal to C delta V. So this right-hand capacitor, our capacitance is 15 microfarads. Delta V is 5. So there's 75 microcoulombs here. So now we know the charge and the potential difference for our 15 microfarad capacitor. For our 5 microfarad capacitor, we currently have the potential difference. Using the same equation, just with information for this specific capacitor, Q is equal to C. So this capacitor's capacitance is 5 microfarads. Its potential difference is 5 volts. 25, but I need to get the right units on here. Microcoulombs is the charge on this capacitor. So now we're back to our original circuit. We now know Q delta V for each of the 3 capacitors that are shown there. Now, a couple of things to point out. I mentioned one already. Let me choose a different color to hopefully get it to stand out a little bit. Let's go with this one. So I mentioned already in circuit 2, if I follow my path from one end of the battery to the next, the voltages of these individual capacitors, that 10 volts and 5 volts, add up to equal the battery voltage. So our conservation of energy, essentially, even though it's not technically energy, we call this a loop rule. If we come back to our original circuit, if I follow this path, so coming out of the battery, I pass this top capacitor. If I choose the path that goes through the 5 microfarad capacitor, it has 5 volts. That gets me back to where I started. That 10 and that 5 still add up to be 15, which is good. That is a required thing. We have to have essentially every element we pass in making our path are all, what's the right word here? They all have a portion of the potential of the battery. So they have to add up to the battery's potential. If I followed this path going up, it's still 10 volts on this first capacitor, but if I came all the way over here, this one's 5 volts. That gets me back to where I started. So I'm still adding 10 volts to 5 volts to get the 15. So that is one thing to check. This making a path, making a loop to double check what's happening in terms of the voltages adding. There's one other check we can make, and that has to do with the charge. If we imagine for a second the charges that we're moving to create an equilibrium in this circuit. Right now, we're solving problems based off of assuming the equilibrium state has been reached, but charges did move to get to this equilibrium state. Let me draw a clean picture at the bottom. So bottom right, so if we just imagine charges moving, we typically use Benjamin Franklin's convention still, even though we know electrons technically are the ones that move. He didn't know the difference between electrons and protons in his time, so he just ran with one. He chose one to work with, and we still use that convention today. In that when charge flows, we account for it in current, such that we are pretending still that the positive current is flowing. It would flow out of the high potential end of the battery and back in after it's gone around the circuit to the negative end. So let's think of this in terms of just the total charge. We know already, we calculated this, that 100 microcoulombs of charge accumulated with that first capacitor. So positives, that would cause induction. So charges would be repelled from the negative plate to in turn come to these two capacitors. But that means there were two paths. So this total amount of charge, when we account for the repulsion that keeps charges moving, the charge that ends up here and then the charge that ends up here has to add up to the 100 microcoulombs. The total charge that flowed, when it reaches a junction, it splits off, not necessarily evenly, but it splits off, and not all charges will take the same path. In fact, they will take the path that will result in these two having the same delta V. Well, we already calculated these. The Q1 is 25 microcoulombs, ended up going to that 5 microfarad capacitor. Q2 we calculated to be 75 microcoulombs, the one that went to the 15 microfarad capacitor, which wonderfully adds up to be this 100 microcoulombs. This is a conservation of charge equation and must be satisfied as well. So a couple conceptual things along these lines to keep thinking about. Just making sure we're following the path, keeping charge the same, or potential difference the same based off of how our capacitors are connected. So this little guy over here that I moved, similarly, we could be given capacitor values, battery values, or a mixture of the values and have an unknown. So let's see. Let's say this is a 9-volt battery. There's a bit of a lag still, so sorry it takes a second for the writing to show up. Let's say we have a 3 microfarad capacitor, a 6 microfarad capacitor, and let's do another 3 microfarad capacitor. Or maybe I don't want 2 of the same. Let's do 12, just to keep them different, so they're easier to talk about. Well, if I've given the battery voltage as well as all the capacitor voltages, I'm going to be asked about the charge or the potential difference or the energy stored. We have not talked about energy yet. Let's talk about the energy stored by the 3 microfarad capacitor. Now, we could ask the energy in any of them, of course, but I'm just trying to cut down on how many steps we're going to be taking. So number 1, energy. Our equation for energy stored in a capacitor is the U sub C. So one way to write that is in terms of the capacitance of our capacitor and then the potential difference for our capacitor. We know the capacitance, that's in the picture, but we do not know the potential difference, nor do we know the charge. So we do need to take those first steps we did in the previous example, where we're combining capacitors until we get to an equivalent where we would know charge and work back. We essentially need to do the same thing here. We have to combine these resistors enough, capacitors. Resistors are next. We have to combine these capacitors enough to get to the point where we can figure out either the charge or the potential difference for this 3 microfarad capacitor. Once we have any 2 of the 3, we can find the third. All right, so to determine series and parallel, I follow my path. If I leave my battery, I immediately have a choice. I can either pass through the 3 microfarad capacitor or I can pass through the 6. But notice, regardless of which one I pass through, I then, to continue my path back to the battery, I then have to pass through the 12 microfarad capacitor. I can totally say that the 3 microfarad capacitor and 6 microfarad capacitor are in parallel because I had a choice. I did not have to pass through the 3 and the 6. I chose which one. What I cannot say is that the 3 and the 12 are in series. That's not true. And that's because I don't have to go through the 3. I can take a path that takes me through the 6 microfarad capacitor and then the 12. But I can't say either that the 6 microfarad capacitor and the 12 are in series. That's not true either, because I don't have to go through the 6. I can go through the 3. So ultimately, we have to take care of this parallel business first before we can then look at something being in series with the 12. We know in parallel we can find an equivalent capacitance by simply adding them up. So here we have a 3 and a 6, so the equivalent capacitance would be 9. We could draw a circuit with the same 9-volt battery, but in place of the 3 and the 6 in parallel, use a capacitor that's 9 microfarads. This other one is still the 12. because that was not in parallel with the 3 and the 6. Now that I'm to this step, I can follow my path and see that I have to pass through both the 9 and the 12. Now, I don't know Q or delta V for either capacitor still, which means I want to take one more step and find the equivalent capacitance. I'm going to go ahead and plug this in my calculator. This one doesn't turn out as pretty as the last one. We get a decimal answer. So 5.14286. That's more digits than I need to, but I want to go a few. So what this is telling me, circuit 1 was the original circuit drawn. 2 is what that first one becomes when we combine the 3 and the 6 in parallel. So now we're going to have a circuit 3 that represents one single capacitor that has a capacitance of this 5.14 and everything else. So this circuit 3, we're now to a point where we have an equivalent capacitance, meaning if I could possibly go by this value of capacitor and connect it to my 9-volt battery and not exceed its breakdown voltage. So every capacitor has a voltage written on the side. It's a breakdown voltage, meaning we cannot exceed that voltage or sparks jump from plate to plate and it no longer behaves like a capacitor. But if I could buy this capacitor and it could withstand 9 volts, then I would have ended up with the same amount of energy with this one capacitor as I would have with the 3 that we started with. That's what we mean by equivalent. Now, in the state where we have a single capacitor that's in equilibrium with the battery, the potential difference across the capacitor will equal the battery voltage. So in this particular case, this capacitor is going to have the entire 9 volts across it. But if I have capacitance, which is what this 5.14 is, that's supposed to say C, delta V, then I can find Q. You might be noticing we're using this equation, Q equals C delta V, a lot. So I'm going to use the C value my calculator already has in it and multiply by the 9. That tells me this capacitor ends up with a charge of 46.286 microcoulombs. It's micro because I didn't put 10 to the negative 6 in for mu. Now, this is not the charge on just the 3 microfarad capacitor. So we're still not at a point where we can just plug some numbers in. But similar to what we talked before, let's now work our way back. This equivalent capacitance was for the 9 and the 12 in series. Capacitors connected in series must have the same charge. And they must have the same charge as their equivalent. So I can come back here and say that both of these have a charge of 46.286 microcoulombs. Now, unlike the last problem we were finding the charge and potential difference on every single capacitor. In this particular case, we've been asked for only the energy of one of them. That one we care about is the 3. So I know the 3 is accounted for in this equivalent capacitance. So this is the only one I'm going to continue back with. The 12, I could totally find the delta V. That's fine. I could find energy, but that's not part of the question. So I'm going to stop as far as the 12 is concerned and just continue with this 9 microfarad capacitor, which was the equivalent for the 3 and 6 in parallel. In parallel, they must have the same delta V. So right now I have charge and capacitance, but I can certainly solve for delta V as charge over capacitance. So that charge I have divided by 9 gets me to 5.143 volts. Okay, the equivalent of the 3 and 6 in parallel has a voltage drop of 5.143 across it. But the equivalent was equivalent for the 3 and the 6 in parallel. And we know when capacitors are in parallel, they must have the same delta V, not only as each other, but also the same delta V as their equivalent capacitance. So this tells me that the 3 microfarad capacitor has a voltage drop of 5.143 across it, which means I'm now ready to plug some numbers in to calculate the energy stored by this capacitor. So the problem is specifically asking about the 3 microfarad capacitor. At this point, I do want to put in the micro. So 1/2, this is our C. The delta V we just calculated needs to be squared. Okay, let me get in scientific mode because I don't want to count my zeros. I'm getting 3.97 times 10 to the negative 5th. Our units will end up to be joules. So a farad times a volt squared is joules. So essentially we have 4 times 10 to the negative 5th joules of energy stored in that specific capacitor. So in the 3 microfarad capacitor. So this one, we didn't stop and find Q and delta V for all of them because we didn't need to. The problem asked specifically for just the one. Okay, so I'm going to do a few more examples in different videos. But again, I highly recommend following the path. I know it seems kind of silly and tedious, but I promise it helps. It really, truly helps in determining series and parallel. From there, the equations aren't terribly hard to use, but conceptually reasoning through, we have to be careful about and intentional about remembering that series, they have to have the same charge. Parallel, they have to have the same potential difference. Okay, so let's move on to some other examples.